S. Chan presents educational video lectures. Difficult concepts made easy. Study anywhere, anytime.
Welcome to S. Chand Academy, and I am Dr. Anmol Bhatia. We are learning the course Applied Thermodynamics, and in this particular video we will be learning about an important concept, that is compounding of the steam turbine.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box.
So the topic is compounding of steam turbines, and we are straight away coming to the definition of this compounding part and why it is required in the steam turbine. So compounding is basically a method in which energy from the steam is extracted in the number of stages. So we have certain stages of steam turbine, and in those particular stages we need to extract energy from there, rather than a single stage of the turbine. So rather than having a single stage of turbine, we can have the multiple stages, and we need to extract energy from the multiple regions so as to improve the efficiency. The compounded steam has multiple stages, right, as it has more than one set of nozzles and rotors in series. So you have a set in which there is nozzle and then there is a steam turbine blade. So you can extract energy from there, and by placing them in particular series, and they are keyed to the particular shaft or fixed to the casing, so that either the steam pressure or the jet velocity is absorbed by the turbine at the particular number of stages. So what happens if the high velocity steam is allowed to flow through one of the rows of the moving blades? Then it produces a single speed of 30,000 rpm. That is particularly very high for any sort of particular practical use. So not only this, when the steam leaves that particular turbine, so leaving losses are very high. So there is a need to incorporate some improvement in the simple impulse turbine for the practical use, and this is particularly used for impulse turbine. And why do we use it? In order to extract more energy and to achieve high performances. This is possible by making use of more than one set of nozzles, or you can say blades or rotors in series, and they are attached to the particular common shaft. Now the same thing, either the steam pressure or the jet velocity is absorbed by the turbine in that particular stage, so that the leaving loss is less, and we have extracted the same value much before, prior to the leaving the steam from the particular operation, and then the leaving losses would be less, and this process is particularly called as compounding of the turbine. So what compounding basically is? Compounding is basically fitting in the set of you can say the nozzles inside particular casing, so that when they are clubbed together, it leads to lesser exit losses and it leads to higher performance efficiency. So you can see that it is a diagram that basically shows the same. You have the shaft on which this impeller blade is placed, and you have those rotating blades, and you have fixed blades placed on the surface, and wherein we put in the steam turbine into it, it gets utilized and it leaves that particular system. It may have leaving losses. So compounding is basically done in industry. You can see that the same in this pictorial presentation, in which you can see there are a number of places in which these fixed blades are there and the rotating blades are placed over the surface. Now there are three basically categories, or the ways in which we can do this. We can have a process of velocity compounding, the pressure compounding, or the pressure velocity compounding case. Quickly, I am coming to the velocity compounding part, and it was proposed by C.G. Curtis to solve the problem of single stage impulse turbine. And basically it uses the same for the high pressure and temperature steams. You have the rings of moving blades which are placed there, and they are separated by the rings of fixed blades. So moving blades are key to the turbine shaft, and the fixed blades are placed inside the casing. So high pressure steam coming from the boiler, it expands into the nozzle first, and then the nozzle converts the pressure into the kinetic energy. So what happens, there is a nozzle placed, and when we put in the steam from the nozzle into the turbine blades, so what happens, the high steam coming from the boiler is expanded into the nozzle first, and then the nozzle basically converts that pressure energy into the kinetic energy. There is an interesting fact to note in this particular compounding, that the total enthalpy drop and the pressure drop occurs in the nozzle. Thereby the pressure remains constant, and this high velocity steam is directed on the first ring of the moving blade. So this high velocity steam is impinged on the particular set of the moving blades. Now as the steam starts to flow over the surface, due to the shape of the blades, it basically imparts the momentum on the blades and loses some of the velocity. So velocity losses are no doubt there, but this leads to a clearer representation. You can see that there is nozzle and there are certain blades placed over the surface. So you can see that there is a moving blade, there is a fixed blade placed on the surface, then you have a moving blade, and this is the velocity with which this is expected, or the shape with which it is expected. So you can see that there is a pressure drop and it becomes constant, and then the velocity increases, and then it is having certain drops, but those drops are not very frequent. So these velocity drops are the same, and you have this initial value of the velocity and the final value of the velocity at the exit. So you increase the value of the velocity part. So this particularly is called as the velocity compounding. So velocity compounding, only a part of the high kinetic energy is absorbed by these blades, and the remainder is exhausted in the next rings of the fixed blade. So fixed blade, what is the function of that fixed blade? Fixed blade is basically there to redirect the steam leaving from the first ring into the second ring part. Now the steam then enters the next ring of the moving blade, and that process is repeated practically so that the energy being absorbed. So that is presented in the figure 1 that you can see. Herein the PI indicates the inlet pressure. I am talking about that diagram in which this PI and P exit is mentioned. So this PI indicates the pressure at the inlet, VI indicates the steam velocity at the inlet, P naught is the pressure of the steam at the outlet, and V naught is the velocity of the steam at the outlet. It is being discussed about the pressure drop and how this velocity change occurs in case of the blades part. Now it has certain advantages, like velocity compounded turbines requires smaller number of stages due to relatively large heat drops at the particular stage. So there are lesser number of stages inside the turbine that cost you less. Initial cost for that is particularly less. Now in this you can see that in 2 or 3 rows wheels are placed, and the steam temperature is sufficiently low, and the cast iron cylinder that may be used, that can be a material saving aspect of the same. There are certain disadvantages of this velocity compounding. The major disadvantage is it has low efficiency, and the steam consumption here is very high. So this is one of the major drawback of this process. So we stop here for a short break. After coming back from the break, we will learn about the pressure compounding and the pressure velocity compounding part.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy channel, and I am Dr. Anmol Bhatia. We are learning the concept of compounding in case of turbines, and so far we have learned about the velocity compounding. Now in this part we will be learning about the pressure compounding and the pressure velocity compounding case of steam turbines. So the case is of the pressure compounding. Pressure compounding basically is done in case of the impulse turbine, and it is called as Ratiu turbine after its inventor, after the name of its inventor. And the main problem that it solves is the problem of high blade velocity in the single stage. So as we have discussed in the previous aspect that the velocity part was high in case of the velocity compounded turbines, and there was a drawback of efficiency losses. So it consists of alternate rings of nozzles and the turbine blades, and these nozzles are fitted on the casing and the blades are keyed on the turbine shaft. This is basically the design of this compounding. Now in this type of compounding, the steam is expanded in the number of stages and instead of the one. So in the previous situation we have seen that the steam is expanded on the nozzle and then the pressure is being dropped by the nozzle. But herein the steam is expanded on the number of stages in particularly in batches or in numbers. So it is done by the fixed blade which acts as nozzle. So the same case that is there in the, you can say, in the reaction turbine, that it do not have nozzles. The same concept is being utilized in the pressure compounding case. So there are fixed blades which acts as a nozzle and steam expand equally in all the rows of the fixed blades. And the steam coming from the nozzle rings are partially expanded into the nozzle. And you can see that there is a partial decrease in pressure of the incoming steam that particularly leads to increase in velocity. So as far as the diagrammatic representation is concerned, you can see that you have this nozzle portion which expands the steam into it, and you have this moving blade, and you have this nozzle again. Then it again expands into the moving blades, and then the nozzle is placed again. So there is a pressure drop, then it becomes constant, then a drop again. So this is particularly related to the pressure drop. And if I talk about the velocity part, so velocity is being utilized at every stage. So you can see that there is an increase in velocity, then there is a drop, then you can increase the velocity, then there is a drop. So initial pressure is Pi, you can check the initial value, and then the pressure drop is this much. Initial velocity value is this much, and then the velocity is being utilized in energy generation, and this output velocity is demonstrated by this V exit portion. So as you have seen that it has to pass through the set of moving blades, and when the steam flows over the moving blades, so all the velocity is being absorbed and thereby maintaining a constant pressure on the surface. After this, it has to be passed through the nozzle rings and again partially expanded, and then it is being fed into the next moving surfaces, so that this process repeats and ultimately leads to an increase in the value of efficiency. So the symbols have the usual meanings, as you can see, but there is a particular disadvantage. The disadvantage is that there is a pressure drop in the nozzle, and because of that it has to be airtight. So we have to maintain airtight environment in order to maintain that pressure drop. And another disadvantage is these kind of compoundings are bigger and bulky in size, because you have n number of sets. You have a fixed blade, then you have a moving blade. So fixed nozzle is there, then again a set of moving blades, then a fixed nozzle, then a moving set, so on and so forth. It increases or makes the size bulky. Now, the last thing is pressure velocity compounded impulse turbine, and this is basically the combination of the two types of compounding. Here, the total pressure drop of the steam is divided into the number of stages, and at each stage, it consists of the number of fixed and the moving blades. So, basically the combination of the two, and each set of the rings of the moving blade is separated by the single ring of the fixed blade. So, in case of the diagrammatic presentation, you can see that each set is separated by the moving blade, and then you have a fixed blade, then the moving blade, then again a nozzle, then fixed blade, then moving blade, and so on. This process repeats. So it's a combination of, you can say, the velocity compounded part and the pressure compounded part. So herein the same thing goes, like there is a pressure drop in a certain manner and the velocity increases at a certain extent. The velocity is shooting at a certain extent and then it is getting reduced at the certain stage. Now there is one last representation and it is an important topic, and that topic is called as a bleeding of the steam turbine. As you can see that on the exit part, water starts draining out from the turbine. So there are certain stages that some wet steam is drained out from there. So this bled, or you can see that the bleeded steam is then circulated around the pipe that leads to the feeding water in the boiler, and then the feeding water is heated using that steam only. So that wet steam which is being blended out of the turbine is reutilized, and during this process the boiler is supplied with hot feed water while the small amount of work is lost by the turbine. So we can utilize that particular steam for a particular operation. So with this we come to the end of the video, in which we learned about the cases of compounding of the turbine. Specifically, we learned about pressure compounding, velocity compounding, and the combination of pressure velocity compounding. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe, and press the bell icon for future updates.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.